Okay, the recording has started. İzzet Hocam, the stage is yours. Thank you.
First of all, I would like to thank to the organizers for this nice winter school, which is organized under the Feza Gürsey Center for Physics and Mathematics. During the 3 days, I'm going to talk on the analytical studies for Hawking radiation, gray body factors, and black hole quantization. To teach the quantization, of course, I will also tell you the quasi-normal modes and their analytical expressions. I mean, how we can drive the quasi-normal modes by using the analytical tools. So, as can be seen under the contents, the first day, which is called Lecture 1, it is reserved for black hole thermodynamics, derivation of Hawking radiation via wave dynamics. So in addition to the traditional statistical derivation of Hawking radiation, we will use the black hole perturbation. We will get analytical wave equations and their solutions. And then I'm going to show you how those exact solutions lead to Hawking radiation. And then the gray body factors. So lecture 1 and lecture 2 might be mixed up. I don't know how much I can proceed today. But at the end of the day, those analytical computations will be linked to gray body factors and then the quasi-normal modes. In the quasi-normal modes, I will also mention the resonance modes, because another structure which are about the frequencies of the perturbed waves are related with the resonance modes, in which conditions we can get them. That point will be also clarified in lecture 2. Then I will most probably continue the quasi-normal modes in lecture 3. Then by using the quasi-normal modes, how we can get the black hole quantization. So some computations about the black hole quantization will be also given, and then I will conclude my lecture series at the end of the lecture 3. So these notes should be considered as pedagogical lecture notes, as has been asked by Soner, who is the chair of this organization. As much as I can, I will give the details of the computations and the steps which are going to be taught. Okay. So the first is traditionally, I would like to give the laws of black hole thermodynamics. So these 4 laws are actually created and studied by Bardeen, Carter, and Hawking in their 1973 Communication in Mathematical Physics paper. The first law, which is the zeroth law actually, it says that the horizon should have a constant surface gravity for a stationary black hole. The surface gravity is nothing but the gravitational acceleration, by the way. So on a surface of a horizon, this surface gravity should be constant. The second one, which is the first law, it's about the conservation of energy. For perturbations of stationary black holes, the change of energy is related to the change of area, angular momentum, and if there's a charge, it could be electric or magnetic, it should be related with that charge as well. So the change in energy, which is capital E, or it can be mass, it is related with, or it is equal to, the surface gravity over 8 pi. So this is surface gravity over 2 pi is nothing but the Hawking temperature, meanwhile. And that is the change in area plus angular velocity, and the times the change in angular momentum, plus that is the potential, electrostatic potential times the change in the charge. So whenever you get a new black hole solution, this first law should also be satisfied, or you have to find the proper definition for the first law for the black hole solution, which are obtained from the theory that you are using. So the first law is a mandatory the law in black hole physics. The second law is about the horizon. The black hole's horizon changes with time should be equal or greater than to 0. So that was the second law of black hole thermodynamics. But this law was superseded by the discovery of Hawking radiation, because the Hawking radiation caused to the complete evaporation of the black holes. So although that is the second law before the Hawking radiation, but now the Hawking radiation can cancel this law, but that should be kept in the mind. The third law is actually very still a debatable law, because what it says, it's not possible to form a black hole with vanishing surface gravity. So since the surface gravity is directly proportional with the Hawking temperature, or the temperature of the black hole, so having a zero temperature is not possible. Of course, the extremal black holes, in the extremal black holes, the temperatures are 0, but they are counted as non-thermal objects. I mean, that is one of the explanation of preserve the validity of extremal black holes. But as I said before, that is still a debatable issue. And even if you look at this International Journal of Modern Physics D paper, for instance, which was published in 2001, even the limits of the third law are still being discussed. In this subject, look, the third law in thermodynamics, for instance, it allows the entropy to be 0, and at the same time, the temperature can be 0. However, in a black hole physics, the T cannot go to 0, according to that third law. That problem was studied by the Singh, Lanston, and et al. In the LJHAP paper in 2010. What did they do? They were using the entropy from the loop quantum gravity, and by borrowing the entropy from the loop quantum gravity and the string theory, they say that, or they prove that the entropy for a Schwarzschild black hole can take such a modified form. So this modified form of the entropy, at the end of the day, it will lead to such a temperature. So, they suppose to prove that when the mass goes to 0, the temperature will go to 0, similar to the entropy. But what did they do? Here, there's one series, as it can be seen here. They put a condition on this series, and they made the entropy as a ln. They connected the entropy to a ln function. By this way, they drive this temperature. Then I did their computation. I drive their computation, and I saw that they made a mistake. This recurrence relation, kind of recurrence relation, doesn't lead this ln function. Then I wrote them an email that you made a mistake. Then they published an erratum, and at the end of the day, they acknowledged me that it's not possible. I mean, when entropy goes to 0, the T should also go to 0. Question is still open. And it's one of the, let's say, debatable issue about the third law. But after that, with my colleagues Halisoy and Pashaoğlu, we applied this mechanism that they created by the Sakallı et al. To another type of black hole solution, which we are going to call it linear dilaton. So in this linear dilaton, I will give the details more in the future slides. But what is main property? Although these linear dilaton black holes are belonging to three different theories: Einstein-Maxwell dilaton, Einstein-Yang-Mills dilaton, Einstein-Yang-Mills Born-Infant dilaton. At the end of the day, they all admit the same type of metric functions. Only that sigma tilde, which is a constant, can take different forms, but this is a constant. So the structure is the same. When you compute its Hawking temperature becomes independent of mass. So what does it mean? This black hole radiates as an isothermal object. I mean, an object which makes an isothermal process, in other words. So this is one of the unique property of those black holes. So when we apply the Singleton et al. Let's say procedure to drive the entropy and the temperature, at the end of the day, we prove that such black holes, when they completely end up, when there's completely evaporated, that there's no any mass about them, its temperature, similar to its entropy, goes to zero. And we have managed to publish it in Astrophysics and Space Science. But for Schwarzschild type solutions, this is still an open question, because, as you know, for Schwarzschild family black holes, when the mass goes to zero, the temperatures diverges to infinity. So that prevents them to be cooled completely at the end of the vaporization. Okay, next. Anyway, since I mentioned about the first of all thermodynamics, over there we have some quantities like angular velocity. I also typed their generic formulations to here. If you have a stationary black hole, rotating black hole, how we can get this angular velocity. But of course, in first law, everything should be computed via the event horizon. I mean, you will get the generic structure of the angular velocity, which is radial dependent, which is a radial dependent function. But at the end of the day, you have to take its r goes to r plus. I mean, event horizon limit. Similarly, the surface gravity, which leads to the Hawking temperature, which is kappa over 2 pi. To get the surface gravity, you need the Killing vectors, which are related with the symmetries of the black hole, as you know. And for any, let's say, well-known stationary spacetimes, we have two Killing vectors. One is time-like, the other one is related with the cyclic coordinate phi. So what is the Hawking's formula to get the surface gravity? We have this square root and covariant derivative of the Killing field, let's say chi contravariant mu field, which is expressed in terms of these two Killing vectors. So when you insert them over there, actually the students can apply it as a practice to prove the surface gravity, let's say, of a Kerr black hole. Because it seems its formula seems easy, but when you apply it, it will take a bit of time, especially if you do it by hand. Anyway, you will get the kappa, and this is the area of the black hole. We are using the spherical part of the metric. So if we put everything into the first law, let's say the m is now my energy, So m plus, you know, in many cases we express the mass in terms of the horizon. So that's why I put it here plus, and T plus ds plus, this is coming from, you know, the energy part and the other parts of the energy. So why I am showing that, why this first of all is important, because to find the entropy, you should use the exactness condition of this this differential. So once you apply the exactness condition of the this differential equation, this entropy will appear in that structure. This is important because many students guess that the entropy is all the time equal to the quarter of the area, but actually it's not. So you will deduce it, or you will prove it at the end of this integration, which is the result of this first law. So for instance, 2 years ago, this is what I searched and found. And when the guys studied the thermodynamics of rotating Bardeen black holes, over there, for instance, the entropy is not equal to the fourth quarter of the horizon area.
Hocam, can I ask a question here?
Sure.
What exactly is the mismatch here? Is it just the numerical factor, or or do we get something which is not simply the area of the event horizon?
The reason is when you have the different fields, okay, coming from the theory, not in the traditional Maxwell or gravitational fields. When you have extra fields coming from extra theories, this entropy starts to be modified. So it becomes different than this famous law of the fourth, or 1/4 of the black hole horizon. So depending on
is it we get a different numerical factor, or
no? It's a symbolical.
Okay, so something different than really the area of the event horizon.
Yes.
Okay.
Yes.
Okay. Thank you.
So this is what I say. And don't jump on that all the time. That your entropy is the 1/4 of your area, because for different theories that be modified. So this is the best checker, let's say, your entropy if you have a stationary black hole, okay? Or that even the first law may be a little bit vary if you have extra energy factors in your theory. And then from the first law, you can get an expression for the entropy. Then you have to compute it to see whether it is 1/4 of your area, or whether there are some extra terms. Okay, so this is what I want to notify here. Anyway, then by the Hawking's pioneering works, actually, there are two. One was published in 1974, and one is just 1 year later. He made a very revolutionary contribution to the, let's say, quantum gravity. And with his works, the general relativity has started to be unified with the quantum gravity, quantum mechanics actually. What he proved, because of the fluctuations near the event horizon of the black hole, and there's a vacuum difference between the spatial infinity and the region near to the horizon. If there's a creation of particles, these are virtual particles, because of that vacuum differences, one of the particle, which is in general the anti-particle, goes in, the other one should, escape to the spatial infinity, and that the one which is escaping to the spatial infinity is called Hawking quantum. And similarly, if this particle creation has happened just inside of the horizon, again, by using the tunneling process, the one can emit to this spatial infinity, and that causes the black kind of black body radiation, and that was made the Hawking very, very, very famous in theoretical physics. Anyway, yeah, so this is what we know. Of course, over there, Hawking used the method of Bogoliubov coefficients computations to prove this Hawking radiation. So, what I am going to show in this lecture series, the same results can be also obtained by using the black hole perturbation. Because this Hawking radiation subject is one of the, how to say, most tested, I mean, theoretically tested phenomena that many different approaches, many different methodologies, at the end of the day, result in the same answer, which means the temperature is surface gravity over 2 pi. But what I am going to show you, when we apply the wave dynamics to derive the Hawking radiation, we will get more information about the waves. I mean, what kinds of waves can lead to Hawking radiation? Are any kind of waves or any kind of waves having any level of energy will admit the Hawking temperature or not? Such questions were, how to say, question marks for not only me, for the other researchers in the literature. And they focus on the wave dynamics to reveal the properties of Hawking waves, thermal waves actually. And also they prove that the temperature can be modified by the frequency of the wave. So I will give them more details in the future slides. Okay, so at the end of the day, this kappa formulation can be obtained by different methodologies or not. That is my concern, especially in today's lecture. So what I do in general, okay, since I am going to deal with the wave dynamics, at the end of the day, I can find the reflection and transmission coefficients of the waves from the black hole. Especially when we get the reflection coefficients, we have a very famous radiation spectrum formula that you know very well, I am sure, from the statistical mechanics. It is a reflection coefficient over 1 minus r, which is actually transmission coefficient. It is equal to the Boltzmann's formula, 1 over exponential omega over t minus 1. So if I can find the reflection coefficient, that leads me, that allow me to find the temperature of the black hole that I am considering. So, so let's start with a comprehensive example. In 2009, yeah, here, we found higher dimensional version of linear dilaton black holes. I don't want to go to its detail, but I will roughly state the general properties of this metric, but its finding it's another story. Anyway, but the main contributors of finding those metric solutions have actually came from Masari Musavi and Halil Soy, and especially I've worked in its wave dynamics in this physics letter B paper. Now, as I said before, such black hole solutions are the solutions of 3 different theories: Einstein-Maxwell dilaton, Einstein-Young-Mills dilaton, Einstein-Young-Mills Bohren-Infeld dilaton. But at the end of the day, we all get the same structure for the metric functions f and the h. H was the, how to say, the radius of a spherical line element. It's actually, its square is, h is, yeah, its square root is the radius of your sphere. And each time we will get such a structure, and f is represented in a higher dimension in that structural form. That sigma is just a constant, and it will vary depending on which theory that you use. And also the event horizon is computed in this manner. So again, it's a constant. So A is constant, sigma is constant. Of course, the event horizon is constant. The structural form of F is 1 minus R plus over R. And we have here that exponent, which is n minus 2 over 2. So phi is a dilaton, alpha is a dilatonic parameter. Anyway, so for each different theories, we express what are these sigmas. But as I said before, at the end of the day, they are all constants. So for wave perturbations, it doesn't make me any difference because I will compute them as constant in my perturbations.
Meanwhile, another simple question. Sorry.
Sure.
It's not asymptotically flat, right? What do you have at the end?
It's not asymptotically flat. And to this end, you have to compute the quasi-local mass. You cannot use the ADM formalism to find the mass. We also computed it in this paper. Maybe I didn't write it here. So if you follow the Brown and York formalism, I wrote it here.
Yeah. Okay. So.
Yeah.
Okay. Thank you.
So so that makes a very non-asymptotically flat black holes or local black holes. Time by time, when we send any article to the journals, referees ask me this question: why you are considering this non-asymptotically flat ones instead of the asymptotically flat? My answer in general to them is that our universe is also non-asymptotically flat. The best model, which is Friedman, Robertson, Walker, if you look at it here, it's also non-asymptotically flat structure. Anyway, now, as I said before, when we computed Hawking temperature simply from this kappa formulation, I also made it as much as simplified here. So anyone can use this structural form to get the surface gravity. The only thing that you have to need is the metric tensors. Okay, so this one is a contravariant form of this killing fields. At the end of the day, it reduces to that simpler form, so that you can also compute the Hawking temperature. The good thing is, as I said before, this temperature is constant and it is independent of the mass. Okay, so then we ask this question ourselves: how much time is needed for complete evaporation of this black hole? So if you know, or if you remember the modern physics, such question is asked or is addressed to Stefan's law. So the rate of mass, decaying of mass in time is equal to minus sigma, which is called the Stefan's constant, area, and the 4th power of the temperature. So for higher dimensional spherical line element, this is my area formulation. You can also find its structure even in Wikipedia. And here the gamma, it stands for the gamma function. So it's one of the well-known, and you can also find its volume form in well-known books. Anyway, then here, since I know the event horizon, okay, I can get the m in terms of r plus. I insert it here, and then I solve the r plus as a function of time. So it's at the end of the first order differential equation. So what we obtained, you see each r plus is expressed in terms of exponential minus time. So this mu2 is also directly proportional, linearly proportional with the time. So what we deduce, what we understand, those black holes can reach to their final states, I mean the extreme states, in an infinite time. Okay, so these black holes will complete their complete evaporization in an infinite time. And but for different black holes, if you apply this Stefan's law, you may find a finite times as well. As I said before, the only thing that you have to do to address the Stefan's law. Okay, then I am going to now to introduce a semi-classical radiation spectrum method. This is the method to compute the reflection and absorption coefficients of a wave by the black hole. For simplicity, we are considering the massless Klein-Gordon equation. But in time, I will extend this Klein-Gordon equation to the massive and charged form. And you will see it later on. And what we do, we will match the solutions in overlap region between the near horizon and asymptotic region in order to find the reflection coefficient. So this statement, this methodology is based on two main papers. One is published by Page, the other one was published by Inru in 1976. So these are the main papers that I am referring now. So by using the symmetry of the metric, because my metric is independent of time, and also the angular part will admit the spherical harmonics, we can apply these answers, because at the end of the day, the unknown will be the radial part. Okay, the unknown will be radial part, and since this is an n-dimensional, n-2 dimensional spherical line element, it will admit those eigenvalues, which is minus L times L plus n-3. So if n is 4, that will be L plus 1. You are very well known. You are very know it, I am sure, from the Legendre polynomials. Anyway, so this is a fixed point. I mean, this is a well-known point. The only problematic side is the age. So L is also known as the orbital quantum number. So when I apply this metric into that box operator, which is known as the Laplace Beltrami operator, actually, we will get this second order differential equation for our radial equation. So now, to analyze the waves, all the time, you need to find the effective potential, because effective potentials will give us extra information about the wave dynamics. So what is the meaning of how I can get the effective potential? We have to bring my radial equation to a Schrödinger-like one-dimensional wave equation like this one. So whenever you can bring your radial equation to such a form, so you can automatically read the effective potential. So what is the problem? The problem is finding such a term, omega square times function. I mean, let's say here it is that. So to do that, and what I do, instead of h, I am inserting two different functions. One is that, the other one is r to the power of 2 minus n over 4. This can be different, surely. But what is my aim by inserting here? You can also get it, to make this omega square alone. Just it will be omega square times function. This is selective multiplier, let's say multiplier function. So this is a multiplier function. Let's say you may say it is just maybe g of r. And then this g of r should be selected in such a way that your omega square should stay alone, okay, for h or for z. So when I computed it, I got it as r to the power of 2 minus n over 4. Also, we will have some first order differential terms in my radial equation. To terminate them, we have to define the tortoise coordinate. Tortoise coordinate, in general, it kills the first order differential equation, first order differential terms in your main radial equation. So it automatically appears at d over f, and this is completely integrable, and we got its value. And also I rescale my tortoise coordinate from r star tilde to simple r star with this scaling factor. And at the end of the day, I catch a relation between the ordinary radial r and the tortoise coordinate. And that will tell me something later on, you will see. Anyway, when you apply those all things, I mean, first applying these functional transformation, then the variable transformation with the help of tortoise coordinate, you will get exactly one-dimensional Schrodinger-like wave equation. This omega tilde is just linearly related with the omega. Here you have just a scaling factor, okay? At the end of the day, this is my effective potential. As you see, it depends on orbital quantum number. As you know, effective potentials are in general depends on the orbital quantum number. This theta is 4 over sigma h square times n minus 2 square. Anyway, let's look at its plots. Before that, we can also check the limits. So this is spatial infinity, limit of my effective potential. And this is horizon. At the horizon, you can also check it from the tortoise coordinate. The tortoise coordinate goes to minus infinity. So the tortoise coordinate is a kind of, magnifier. It extends the horizon to spatial infinity to minus infinity to positive infinity. So we can see the details much more with the help of the tortoise coordinates. Anyway, so the important thing is that at the spatial infinity, we have a step, the potential step, potential barrier. So if the waves is expected to reach to the observer, if the observer here, the waves should pass this barrier. This is the final barrier that the waves must be high. The waves energy should be higher than this value. And as you will see later, when I get the analytical solution, this expression will appear itself in the exact solution. But for a while, please keep it in your mind. And also, since the potential is 0 near to the horizon, and if you remember our one-dimensional Schrodinger-like wave equation, so the potential, that is 0. So what kind of waves do we have? We will have plane waves, because right-hand side is gone now. So near to the horizon, we will have plane waves. Is it a surprising result? I think no, because near the horizon, the gravitational attraction is so high that all the waves started to act as plane waves. So we will have two kinds of plane waves. One is called ingoing. The other one will be outgoing. Okay, how I decide if it is ingoing and outgoing? Actually, this x here can be tortoise coordinates. If the difference between the time and the tortoise coordinates is negative, it is called outgoing. If it is plus, it doesn't matter the overall is positive or negative. You don't care it. You just check the difference between the R star and the time, whether it is positive or negative. If it is positive, it is called ingoing. So this is how we decide whether we have ingoing wave or outgoing wave near to the horizon or anywhere. Okay, next. Okay, so then we started to think, can we solve this radial equation exactly? And then we realized that, yes, it is possible. So, and we saw that this is one of the part of, one of the sub solution of hypergeometric functions, which is called Gaussian ordinary hypergeometric function, which is denoted by 2f1. And this above one can be brought to this structure. When I come to the rotating version of this linear dilaton black holes, I will also give more explanation how one can reduce the radial equation to a hypergeometric function. So I will give you more hints in the future slides. So please be patient about it. So, but how we can bring it to this structure, I applied, first of all, variable transformation, okay? This variable transformation is called also as homotopic transformation. The problem is all the time is this power, which is, we call it in general alpha. But for here, if this alpha is selected as 2 over n minus 2, and if we furthermore say, okay, this expression is my lambda tilde square, and that was the this one, okay, the above radial equation takes the following form. Okay, it takes the following form, and also let's say this small delta is my square root omega tilde square minus lambda square minus 1 over 4. Look at here, this lambda square, if you remember, minus 4, it was my barrier. It was my barrier for the effective potential at spatial infinity. And you see the wave of the energy of the waves, frequency of the waves, minus we get now the barrier. So what does it mean? In order to have this sigma real, this omega tilde square should be greater than this one, which is exactly the barrier of the effective potentials. And this is what I expected. This is what I observed from my potential graph. Now, this sigma, when we solve it, the differential equation, it will solve it, it will show up itself in the hypergeometric parameters. This is A, this is B, this is C. And you see that has a, that delta and omega tilde, they are all the time together. So one should be the winner, and the winner will be, must be, as we will see it later, should be omega tilde. When it comes to the reflection coefficient computation, that will be more clear. Anyway, those rho and tau will appear like this. These are just abbreviations, okay? Then I am going to test it, okay? This generic solution when the wave come closer to the horizon. When the wave come closer to the horizon, we will see that our wave solution becomes this one, C1, okay? Because when R is equal to R plus, you see, when R goes to 0, by the way, do you know this? I mean, if the variable of the hypergeometric function is 0, what you get? You get 1, okay? So near to the horizon, these hypergeometric functions, just they are 1. So you only have these 2. I mean, the coefficients of the hypergeometric functions. And when you set up those things in this form, you can show that, okay, this is my outgoing and this is my ingoing, because the general solution should also result in plane waves near to the horizon. And this is what I got now. Then I would like to extend my solution to the spatial infinity. So spatial infinity can be obtained by this transformation, okay? Because if y goes to 0, r, which means infinite. So this is obtained from the, if there's any question. Okay, if you have any question, just unmute your microphone. Anyway, so I am using this inverse transformation of the hypergeometric functions, and I move my general solution to the infinity. And when we come here, this y, when r, this 1 over y, yes. When r goes to infinity, 1 over y will be 0, and again my hypergeometric functions will behave as 1. So at the end of the day, I will read the this is ingoing, because the both of them this is outgoing, because the difference is negative. Now the difference is positive, and this is the ingoing. So I can find which one is ingoing and which one is outgoing. So what are these B1 and B2? Actually, they are expressed in terms of C1 and C2. Why? Let me come back. I am going to apply this transformation for each hypergeometric expression here. I mean, each hypergeometric function will be transformed to that form. Therefore, this gamma functions multipliers here will be multiplied by C1 and C2 in each time. So this B1 is appeared as like that. The B2 will be this. Okay, so I will find the B1 and B2 exactly in terms of C1 and C2 that we obtained for general solution. Here also, because of this transformation, the A's, B's, and C's will be also modified, which I am calling them A hat, B hat, and C hat. They will take those forms. Okay, now, so I am now suppose sending one wave. Okay, it will go to the one of them is going into the black hole, and the other one will reflect. Okay, as Hawking radiation. So this is called inverse scattering method. And in the inverse scattering method, I only need ingoing wave solution at the spatial infinity. So what does it mean? B1, 0 conditions should be applied, because this is my scenario. So when B1 is 0, you can find a ratio between C1 and C2. So what is the reflection coefficient? If you look at here, it is C1 over C2, of course, in magnitude forms. Sorry about my cough. Okay, so this is the reflection coefficient that I can obtain. So it appears as in terms of A hat in gamma square and square. And this is A hat minus C hat plus square and square. So what are those gammas in terms of trigonometric functions? Because again, if you look at the Abramovich and Stegan book, each gammas like half plus imaginary mu is, and their magnitude square will be pi over cos pi mu. So I am going to rewrite my reflection coefficient with the help of this identity. And I got my reflection coefficient in this way. Then I am going to use my reflection coefficient in the radiation spectrum formula. So when I insert it into the radiation spectrum formula, my whole aim is to get the temperature, because that was the Boltzmann formula, so that I got the temperature as a function of frequency. So the question is, okay, how about Hawking temperature? So when I can get the Hawking temperature, if I know this the generic or the temperature function, it's a function of frequency, because then what we observed, if I use the high frequencies, when I use the high frequencies, this delta, if you remember, it was omega tilde square minus lambda tilde square minus 1/4. So in the high frequency, I mean the omega, when the omega tildes are very, very high, that becomes dominant, and delta and omega tilde becomes identical. And if you insert them here, and then, you know, the cosh, it is exponential, you know, this is exponential minus 2 pi omega plus over 2. Anyway, so that becomes again the dominant. So if you put everything into the form, okay, and remembering that this omega tilde has this factor, at the end of the day, you exactly get the Hawking temperature. So what does it mean? What the wave dynamics tells us that not all the waves can be observed by the observer as an Hawking temperature. The ones who have high frequencies will be detected as Hawking temperature, and this is nothing but the Hawking temperature computation from the statistical methods that kappa it was here, this one. Okay, so my or our computations now are in harmony with the computations of Hawking's original work. So, but we have more information here that only in the ultra high frequency regime, this temperature can lead to the Hawking temperature, which was obtained from the statistical Hawking temperature formula. Okay, so this is what I got from the wave dynamics, and even this is in higher dimensional. So the n can be here greater or equal to 4. Okay, any question? If not, I will continue. And as you see, these are the graphs. This is the T versus omega, I mean the frequency graph. So when we increase the frequency, they all meet with its standard statistical Hawking temperature computation. So even the temperatures are in different theories, but at the end of the day, higher ultra high frequency regime make them Hawking temperature. So low energy waves cannot be detected by the observer, in other words. Okay, then we extend our computations to other dilatonic black holes with double horizons. That was our paper published in Classical Quantum Gravity in 2010. This time, instead of one single horizon, we will have two horizons. Over there, we use Einstein-Maxwell dilaton theory with double Liouville type potentials. So each lambda is the parameter of the Liouville type potential. Anyway, we found the metric function. Meanwhile, we also got electromagnetic potential. So our black hole is charged here actually, and that is a corresponding Maxwell tensor. Then we wrote this black hole. We wrote this black hole in a more how to say user-friendly form. We wrote it in terms of R2 and R1 because we know that R2 and R1 are the constants at the end of the day. They are independent of radial coordinate. The B is also the constant, but there must be a condition that this B must be positive. Otherwise, we cannot get a black hole space-time. And the R2 and R1 was also obtained in terms of the theories parameters A, B. Anyway, but this structure is important. This is my F. And also, I have one more thing, just a minute, let me go back, maybe we forgot it. Here we have R square, but this R square is where, here. This R square is, again, a constant times R. So that's why we call it linear dilaton, because whenever the, how to say, the coefficient of the spherical part is in the R form, not R square, these structural forms are called linear dilaton because their dilatons are also linearly dependent on R, because ln is just a scalar, like a tortoise coordinate. Anyway, then we applied again our ansatz, but what I do, this time I have two unknown functions. One is radial functions, the other is the angular functions. We compare with that, let's say, dagger, or how to say, the pound symbol. Anyway, and at the end of the day, we got this angular equation. Again, I am using now massless Klein-Gordon equation. We got this structural form. This is actually well-known differential equation, which is called the spin-weighted spheroidal harmonics. But this spin weight now is just replaced with P. So what is the P? P is just, massless plus charged. You see, this is charged because here my covariant derivative is partial derivative of mu minus I cube times what electromagnetic vector potential components. So when you change your covariant derivative to that structure, that means you are considering charged and massless Klein-Gordon equation. So in this, for this Klein-Gordon equation, we solve the system completely and exactly. Anyway, so this P is Q times Q, okay? Here, that just is the spin weight of my spin-weighted spheroidal harmonics. So that angular part is okay. So that lets me, that gave me what eigenvalue, which is L times L plus 1 minus P squared. So you may just Google it. You can find the spin-weighted spheroidal harmonics main differential equation, and you can just match it with this separated angular equation. At that moment, you can read that what is your eigenvalue and what is your spin weight. So you will see that my findings will match with yours. Anyway, Then how about the radial equation? We also got it in terms of hypergeometric function. So again, we will have the full solution. Here we have A, B, and C. But as I said before, finding the mathematical solution, it makes sense, but we have to make it more richer by applying some physical methods, and we have to get some outcomes from this solution. So again, we use, here, that sigma is, again, you see, it appears as in terms of energy, I mean the frequency. Here, again, here we have this part. So this omega square should be greater than this second and the third terms. Anyway, and also in the expression, the solution that I obtained, omega tilde is omega n tilde, and tilde is this one. And setting R minus R2 in this structure, I first of all get the near horizon solution of my psi. Why I am doing that? Because I would like to get which one is ingoing, which one is outgoing. Here, wait a minute, most probably I made a mistake somewhere in the signs. C1 is near the outgoing, so this is plus. Sorry, yes, that should be plus. And both of them are negative. Yes. No, that is okay. That is okay. Sorry, that is okay. Yes, now it's okay. Anyway, so we got the outgoing and ingoing waves. Again, we have to extend the solution to the infinity. To extend it again, I used our inverse transformation for the hypergeometric one. Then each hypergeometric function in the general solution should be transformed to that form. So you will have 4 hypergeometric functions later on, okay? But they will be combined, don't worry. And at the end of the day, and each 1 over z is here at the spatial infinity. This 1 over z will be go to 0, and hypergeometric ones will be 1. So we will not deal with the functions, we will deal with the coefficients, okay? And at the end of the day, we will have B1 and B2. And these B1 and B2, as we did before, they are connected with C1 and C2. Now, that needs a little bit algebra, but at the end of the day, if you make a straightforward computations, you will get them. So you will have B1 and B2. Again, this is outgoing, that is ingoing. But what we want to send the wave from infinity, and we want reflection at the event horizon as an Hawking quanta. So B1, according to this semi-classical radiation spectrum, this B1 should be terminated. So when you terminate it, you get a relation between C1 and C2. So the ratios. So which is called a reflection coefficient. So this time my reflection coefficient is a little bit complicated, but at the end it is expressed in terms of Cauchy's. So when it is expressed in terms of Cauchy's, and by using this generic property of the gamma side, this is what I did here, I can find the resulting radiation spectrum again, and this T now can be obtained. Actually, yeah, that is more, better. This is general actually. The temperature is just omega over ln 1 over r. So when we inserted everything here, we get a temperature in terms of frequency. But again, I will look for in which case this temperature will exactly the temperature of the black hole, which is coming from the statistical mechanics of Hawking's original work. Then we a little bit surprised because when we made our computation from the standard Hawking temperature, which is called statistical Hawking temperature, in other words, the Hawking temperature is in this structure. So we have constant B over 4 pi 1 minus inner horizon over outer horizon. But when I apply the ultra high frequencies, I mean, when the omega is very, very high, that it dominates everything, we saw that this temperature is just B over 4 pi. So it corresponds to extremal case, I mean, extreme states that R1 is 0. So this is nothing but the Hawking temperature of the static linear dilaton black hole, not the double horizon one. Then we thought, okay, how it is possible, so, or how we can find, yes.
Well, I'm just asking for clarification. In the extremal limit, I should have R1 is equal to R2, so I should have 0.
No. I made a mistake. R1 should be 0. So when the R1 is 0, look at here.
Okay, you are going to the previous solution. That's why. Okay.
Yes.
Okay.
The A, yeah, I made it here. The A1 should be 0. Okay. So this is not the extremal black hole. That R1 should be gone, and we will have only one horizon solution again. But this is only in the ultra high, very, very ultra high frequencies. Then we have thought, when we can get this statistical Hawking temperature one, so what is the criteria? Then what we discover, okay, this sigma, look at here in the cosh, you have this omega plus omega sigma plus omega over B, R2 plus R1 over R2 minus R1. So everything is lying here. Okay, the sigma will be greater than omega over B, and the both of, I mean, sigma and over this term should be comparable. I mean, omega should not be completely the dominant. So if it is comparable, but the both of them are much more greater than 1, okay, then we saw that it exactly goes to the statistical Hawking temperature 1, okay? So the sigma, it was also related with, if you remember, let me, here, let me a little bit, yeah. Yeah, the sigma is also responsible from here, the omega. So they are comparable, and the both of them are greater than 1, but omega should not go to infinitely large, okay? They are big, how to say, they are not infinite. So in this case, because their sigmas are canceling each other, and at the end of the day, we exactly get the statistical Hawking temperature. So what does it mean again? Not only every waves, or not only very energetic waves will come to the observer as Hawking temperature, I mean, as a thermal radiation. Only the waves which are energetic, but which are a little bit less than the sigma, and this the sigma is, as you see, it varies the energy of the wave, okay, because of this theory parameters, okay. When they are greater than 1, much greater than 1, we will get the Hawking temperature. So the wave dynamics tells us that only selective waves can be detected as the Hawking temperature. So why this Hawking temperature is important? Of course, now theoretically, we know that or experimentally, we know that their detection is very, very difficult, because when you pass to the SI unit system, even those frequencies are very low actually. But who knows, maybe in much future, such sensitive devices may be constructed. And because of that thermal radiation, we will have a right to recognize which type of black holes that we are detecting. We will detect the black holes, and now, but we can only say, okay, it is Schwarzschild type, maybe, or stationary ones. But in theory, now we have many different black hole solutions. So to make their difference, we need an observation. So maybe similar to the gravitational waves, thermal detection also will help us to classify the black holes that we will detect. So this is in this concept, I think that frequency-dependent temperature will be helpful to us. Okay, the rotation version of these black holes. Okay, I think many of you are familiar how to make the stationary form of a static black hole solution. What we do in general, we apply that Newman-Janis-Winokur formalism. However, such formalism is not valid all the time, especially when you have non-asymptotically flat geometries. So these guys, I mean, actually the father name of the linear dilaton black holes. Let me show their names: Clement, Galtsova, Lignac. If you look at their that PRD paper, that's why I am all the time using the linear dilaton black hole name, because first they call it like that. They show that, okay, if you like to find its Kerr extension, you have to apply a kind of symplectic matrix transformation. So they use the Kerr as a basis, and then they describe a very special transformation that they convert their static black hole, linear dilaton black hole, to a Kerr type stationary ones. And this is that 320, 321, and 322. These are the final answers, and this is called the rotating linear dilaton black holes. A is the rotation parameter here. M is the mass parameter. R0 is the charge parameter.
Is this just the usual Neyman-Janis trick with, I don't know, matrix notation, or well, it's a generalization, I guess.
Yes, it's a generalization. And if you have any experience about that symplectic matrix transformations, I suggest you to look at this paper. They also use, harmonic mapping, and it's maybe 2 or 3 pages are reserved for this transformation. Anyway, even I couldn't get it. I asked them how to get them, but there are many secrets. But okay, what I know,
let me ask at least this, because this is important for me. As you said, Neyman-Janis, it doesn't have to work, right? We have to check it then.
Yes, so, it doesn't work here.
Is it also the same for this method?
For this?
So somehow they generate a metric. It might work and it might not work, and then I have to check it explicitly. Is it the same for this method?
According to them, that Neyman-Janis-Winokur metrics are working for asymptotically flat ones, not the ones like this that they are produced from, dilaton fields, because dilaton and axion fields causes to non-asymptotically flat structures. So this formalism, Neyman-Janis-Winokur formalism, fails over there. So that's why they apply such a symplectic matrix transformation. So somehow they use the asymptotically flat rotating metric, and they transform it to the non-asymptotically flat ones by taking static ones by this way. Somehow they achieve it. Actually, as I said before, I couldn't get it. But what I know, when I insert their metric functions into the Einstein field equations, dilaton equation, which is a scalar equation, and Maxwell equations, now it works. And their solution, obtained solution, works very nice without any problem. So the technique that they are using needs to be worked on it. But what I said, just taking the static version of the linear dilaton black hole, you cannot get its rotating version with a well-known Newman-Janisch-Winokur method because I applied and it doesn't match.
Okay, thank you. Yeah.
So keep in your mind, maybe you may work on it. So this, by the way, this is axion. It's not the surface gravity, and that's the dilaton. By the way, if there are some PRL papers that and maybe in a Washington University, there's a group, I forgot their names, but they are making an experiment that this dilaton and axion fields are the candidates of dark matter. So you just Google it and you will see that, okay, it's they are developing their setups, okay? So this dilaton and axion plays a very important role. And especially when I talk with the Clement, according to him, what it says, since the majority part of our universe is made by the dark matter and dark energy, so this is the black hole, because of this dilaton and axion, is the one which is rotating in the dark matter, different than the curve. And thinking about just making a simple logic, he might be right if this dilaton and axion are the good candidates for dark matter. So this can be thought as one rotating black hole in dark matter or dark energy, but the strange thing is that this dilaton and axion are valid or are appearing itself because of charge of the black hole and rotation of the black hole. So they are not, they don't have their own extra parameters here, own characteristic parameters. So this is how he interpreted their solution. Anyway, so what do I want to do? I would like to write this solution in more familiar form, which is a Boyer linguistic structure, which we have here delta. So this delta is just r minus r plus r minus r minus, like the curve. Okay, and here we have r0 r. When we compute the quasi-local mass, this is the quasi-local mass. You see that this m is related with the mass parameter. It is just the double of the m is seen in the here for horizons. Okay, it's just the double of the quasi-local mass. We can also get the angular momentum. It is also computable. It is just 8 times r0 over 2. So it satisfies, of course, the first law of thermodynamics. This is one thing. I consider this metric in one of my PhD paper, and I solve it exactly. It's a Klein-Gordon equation having charge and mass. I will also give its solution in my future slides. But what I also did over there, I computed its temperature from the acceleration. Because as I mentioned before, the surface gravity is nothing but the gravitational acceleration. I mean, if you compute the surface gravity for our Earth, you will get G. So how I can get the acceleration, particle acceleration in the influence of the compactified object, we can use the forward velocity by using the Killing vectors. So this forward velocity is written like this. Okay, we have here two Killing vectors, and of course it must satisfy the normalization condition, this forward velocity. So one can easily see that this ut, because the ut will be 1 over root gtt, because ut is something like this. Okay. Anyway, then that is the definition of the particle acceleration if you compute the Christoffel symbols. Which is just this one. I mean, any introductory GR book, most probably you will find its definition. And the kappa, this is in the Waltz book. The kappa is also written in terms of this is a actually, because this is a square under the root over that ut component of your forward velocity. If you compute it like this, okay, by knowing that that is your ut, you will see that the kappa is just f prime over 2, which is r plus minus r minus over 2, r plus r0 for this space-time. But this is generic, I mean, or that is a more generic structure for the surface gravity. And you can get the Hawking temperature again by using its famous formula h bar kappa over 2 pi. Okay, so this is another computation of the kappa instead of using that covariant derivative of the Killing field. You can go from the particle acceleration. Anyway, if you check this article, you can see its detail also over there. Anyway, this, as I said before, it's a rotating black hole. At the end of the day, it must satisfy the first of all thermodynamics. So, but instead of the ADM mass, now you will have quasi-local mass. Okay, so because still it's a non-asymptotically flat black hole. And this is the Hawking temperature. It's entropy change. Here we have what horizon, the angular velocity at the horizon, and we have here angular momentum. Anyway, when you do everything, you see that it also passes this, how to say, test that my rotating black hole, which is a rotating linear delta black hole, satisfies the first of all thermodynamics. Again, if you apply this, the integration formula that I showed in the previous slides, you will see that this entropy is just A over 4. So everything is fine. I mean, once you put it into the first of black hole thermodynamics condition, you will see that that solution satisfies this Montantori rule. Anyway, now we would like to solve it. We would like to solve its Klein-Gordon equation for a massless particles. Okay, again, I introduce my ansatz for the test scalar field. By the way, this is the Klein-Gordon equation, and this is a test field. Well, what is the meaning of test field? When we have this wave propagating in the space-time, we are ignoring the back reaction effects. This is not the Einstein scalar wave equation. This is just a scalar wave equation. So we are just assuming that the waves are, or the scalar particle is moving in the wave, the geometry, but the geometry is not modified because of its motion. Otherwise, the problem becomes more and more complicated. Among them, the most hardest one is the Einstein-Dirac field equations. Once a time I was dealing with them, really getting their analytical solutions seems impossible. Maybe one day with how to say, improving mathematical tools, it will be possible. But for such a black hole solution, it seems impossible. Anyway, so when we insert them, when I insert this ansatz into that Klein-Gordon equation, I get this radial equation. So the important thing is here is this. It seems simple, but very effective variable change. And this variable change after this one of my paper that I published in 2015. From 2015, many authors similar to me have applied such transformations to the wave dynamics, and it yields promising solutions. So R minus R plus over R minus R minus. Okay, so when I insert it over there, so when I change my R to the Z, so you can leave the R alone, and you can express the R in terms of that, you can get such a structure. Okay, now, so this is okay. This is in the form of hypergeometric functions. This is also okay, but here is headache, you know, because normally you don't want A and B if you want to reduce your radial equation to the hypergeometric ones. So when you make the solution after some straightforward computations, you can see that A, B, and C for this black hole, for this radial equation, can be written in that forms, in most compact form. But as I said before, yes.
Can you wrap it up in a few minutes, please? We are running out of time.
Sorry?
Can you wrap it up within a few minutes, please?
Okay. My time is finishing?
Yes.
Okay. Just 2 minutes, okay?
Okay.
Thank you. I really didn't care the time. Thank you so much. Anyway, so that will be good point for stopping. You see, in this paper, I also publish an appendix, and that may be also instructive for the students who listen to me today. Okay, so what you do when you meet with such a form, it likes hypergeometry, but actually, or any well-known differential equation, but there are some problematic terms. So what we do, we express, or we let, okay, y to the power of alpha, 1 minus y to the power of beta, and unknown fy. So when you insert this as homotopy function into the expression, you will see that there are some relations between A and these exponents. Okay, so since these A tildes, B tildes are headache for me, I select alpha and beta, those exponents, in such a way that they will be constant. So this is how we can find the exponents, okay, of the ansatz which leads to the hypergeometric equation, or any equation that you know. So when we do it, we can, you know, reduce the this, let's say, 62 to 71. So we determine the exponents of y and 1 minus y. And then this structure gives us the exact solution of my radial equation. So that is how we determine the exponents of S homotopy transformations. Anyway, so it's a good point, I think, to stop here. Thank you, Soner. Tomorrow, I will continue from here. And we will pass to gravity factors and resonance modes, and then the quasi-normal modes.
İzzet Hocam, thank you so much for this
Let me stop my sharing.
Before we stop the recording, is there any question?
Yes.
Are there any questions from the audience? Okay, sounds good. Then I'm going to stop the recording.